We were just looking at the Dirichlet distribution, which is a distribution over probability mass functions on a finite set. And in this video, we're going to compute the expected value for one of the coordinates of a Dirichlet distributed random variable. So this was the definition of the density of a Dirichlet. So let's rewrite that down here. So the density, probability of theta equals 1 over, let's go ahead and write out what that beta function is. It's just the gamma function of alpha 0 times the product of all the other gamma of alpha 1 times gamma alpha 2 up to gamma alpha n times the product as I goes from 1 to n, theta I to the alpha I minus 1 times the indicator, theta in s. And this gamma function, so we're going to try to prove this. This is going to be our goal, to prove this expected value. And a property which is going to be useful, I thought about this a little bit ahead of time, is that the gamma function satisfies the following property. Gamma of x plus 1 equals x times gamma of x. The gamma function is actually, this can be, x could be a complex number. In fact, it can be extended to the whole complex plane. Well, it's meromorphic on the complex plane. But for our purposes, we just need x to be a positive number. And so this is true. This is just a property of this gamma function. You can look up the gamma function if you don't know what that is. And we're going to use that. So let's see. Let's look at the expectation of theta I, and that's just, of course, the integral over all thetas of theta I times this density. And this d theta here is, I'm just integrating over each of the coordinates. So I could write d theta 1 times d theta 2, etc. up to d theta n. And since the density only has support on the probability simplex, in fact, this is an integral only over that part of the thing. But you could make it the whole range of r or something like that if you wanted to. So what is this? Let's write out. Well, let's plug in our definition here. Maybe I'll leave a little space. I think we're gonna. So let's put gamma alpha 0 n times this product, and we have alpha I, or let's make this, I don't know, let's just do it for what? For the first coordinate. And this argument will generalize. So if we do that for the first coordinate, we get in the first coordinate we get alpha 1. Let's pull out the first one. Or I guess we could say it this way. This equals no, yeah, let's do it that way. Okay, so let's put the first one in here. Let's put this theta 1 to the alpha 1, and since we're multiplying that, then we just get that gets rid of the minus 1, and then we have the rest of them. Theta I to the alpha I minus 1. Okay, now my plan here is to make this look like a Dirichlet distribution, but with a new alpha. And the new alpha will have, or let's say beta. Let's say beta has beta 1 equal to alpha 1 plus 1, and all the others, beta I, are just alpha I. And so that will look like this part. If we put the betas in, it will look like, if we put betas in here, we would get this. But we need to fix these guys. So we need to get betas over here, and in order to do that, we need to we're going to use this property. So gamma of alpha 1 we need to get rid of that. So let's use this for x equals alpha 1. So that's equal to alpha 1 times gamma of alpha 1. And so if we use this in here, let's see, so what do we want to do? We want to, maybe if we multiply, well, let's not put it in there quite yet. Let's make a new line to use these new things. So this will be, so that'll take care of this one. And then we can just put beta in for all the other parts of the denominator here, beta instead of alpha. But then we also need to take care of this guy, because the sum of the betas, beta 0, we want to get beta 0 in here rather than alpha 0. This is equal to the sum of the betas. And this is 1 plus the sum of the alphas, right? So we want to get alpha, we want to replace this with 1 plus alpha 0. So for that, let's see, we want to get alpha, alpha 0 plus 1 is equal to alpha 0 times gamma of alpha 0 plus 1 equals alpha 0 times gamma of alpha 0. I think that's going to be good. Okay, now let's make a new line, and we'll plug in this stuff. So this one becomes, we solve for this part, this becomes gamma of beta, right? This is gamma of beta 0. And then we have to divide by alpha 0. This one, gamma of alpha 1, when we plug in here, we solve for gamma of alpha 1, we plug in, we get alpha 1 in the numerator divided by gamma of beta 1, because this is gamma of beta 1, that's a 0. And then we get all the other, since alpha I equals beta I for all the others, we get just betas here. Now, alpha 1, I guess I could write here, this is alpha 1 plus 1 minus 1, and this is beta 1. So this becomes alpha 1 to the beta 1 minus 1, and then we just get the rest of them. Product as I goes from 2 to n, alpha I to the beta I minus 1. And this is just exactly the density of a Dirichlet with beta, with parameter beta, right? That's this part. So this equals, so this all, we can pull out, this is just a constant, it doesn't depend on theta. So we can pull that out. And since any density function has to integrate to 1, all of this stuff, it just becomes 1. So the integral just makes all of this 1, and this is our answer, alpha 1 over alpha 0. So that means the expected value. So we could do the same thing for any of the others. We just did it for 1 here, but it's not too hard to see that you could use the same argument for any of the others. And we would get that the expected value of the ith coordinate is just alpha I divided by the sum of all the alphas. And that is exactly what we wanted to prove. So that's how you compute the expected value of one of the coordinates for a Dirichlet distributed random variable.